Thank you. I'm Norbert Morgenstern, Chair of the FUNDÃO Tailings Dam Review Panel, which today issued its report on the immediate cause of the failure of the FUNDÃO Tailings Dam on November 5, 2015. Following that event, Samarco Mineración and its shareholders, BHP Billiton Brazil and Vale, instructed the law firm of Cleary Gottlieb Steen and Hamilton to conduct an investigation into the immediate cause of the failure of the dam. Cleary Gottlieb established an expert review panel of 4 geotechnical engineers, including myself, to analyze the failure and provide our independent and unbiased professional judgment regarding the immediate cause of the failure. In the next 30 minutes or so, I intend to give you an overview of the panel's report, including the history of the FUNDÃO Tailings Dam and the reasons for its failure. There will be time for questions following my presentation. And of course, I would urge you to read the report in its entirety, as it goes into much greater detail on the topics that I'm about to discuss. In the next slide, we'll look at the orientation of the dam in order to become familiar with some of its features. Here we can see the sides of the FUNDÃO Dam, called the left and right abutment. That nomenclature is based on looking downstream, right being on your right looking down the valley and left on the left. We see Dike 1 and Dike 2, which were intended to provide reservoirs for sand and slimes. We see the toe of the dam, and we see the crest of the dam. We also see a feature called the setback, which will be discussed in some detail later on. We see lines indicating the berms on the dam, which are segments associated with its raising, and the dam at the time of the failure was approximately 100 meters high. The FUNDÃO Dam collapsed during the afternoon of November 5, 2015. Around 2:15 that afternoon local time, many in the Samarco facilities felt an earthquake lasting several seconds. Approximately 90 minutes later after the earthquake, at 3:45 p.m., reports that the dam was collapsing began. There were several eyewitnesses who observed the collapse of the FUNDÃO Dam, and their observations offer the best insight as to how and where the failure was initiated. The subsequent slide synthesizes the sequence of events at the left abutment as observed by the eyewitnesses in a somewhat chronological order. First, dirty water was discharged from a blanket drain that existed in the structure. Secondly, the plateau moved forward in a downstream direction. Thirdly, there were observations that large slope deformations, rather like a wave, began to occur from the bottom up. Fourthly, there were observations of a crack forming at or about the elevation 875 meters bench. The eyewitness observations established several critical things. First, the failure of the dam started at the left abutment, not at the middle, not at the right, not at the toe, but in the left abutment as indicated. Secondly, the failure occurred due to a flow liquefaction of the tailings. The tailings lost their strength and behaved like a liquid flowing out of the dam. And finally, the observations show that this transformation from solid to liquid was abrupt. Let me stress that the size and impact of the failure of the dam was not so much because the dam had failed, but because of the fluidity of the materials which liquefied so completely. Had the dam simply moved or slumped, it would have had consequences, but not anything like the consequences that it had. The panel regarded the essentials to explain what happened embodied in answering 3 questions. First, why did it occur, meaning why was the event a liquefaction flow slide as opposed to some other type? Secondly, why did it occur where it occurred, meaning why did the flow slide occur at the left abutment and not the right abutment as unambiguously declared from those who were there? And finally, why did it occur on November 5, 2015? In order to answer these questions, I want to share with you some relevant events and conditions that developed at the FUNDÃO Dam, beginning with the conceptual design for the dam. As you can see in the next slide, the plan for the FUNDÃO Dam envisioned two starter dams, Dike 1 and Dike 2. These starter dikes would dam the FUNDÃO River and valley and permit mine tailings, both sands and slimes, to be stored behind them. If we could slice the dam open, in the next slide, we would see a cross-section of the facility. Slimes would be stored behind Dike 2 and the sands behind Dike 1. In this way, the sands and slimes would be physically separated, an integral condition of the design. Over time, the sand tailings themselves would be used to increase the height of Dike 1. This method of raising is known as the upstream method of construction, whereby the construction proceeds in a method that sits over previously placed material. To maintain the separation between sands and slimes, the dam design required the sands behind Dike 1 to be separated from the slimes by a 200-meter wide beach, as shown in the next image. Maintaining the beach behind Dike 1 was necessary to hold back the slimes as Dike 2 was over top, and to do so, the design specifically required a 200-meter wide beach. In addition to the separation between the slimes and sands, FUNDãO's design called for a drainage system that would keep the sands drained, meaning that water would flow freely downward through the sand facility and allow it to be emitted at its base, and the sands would not become saturated. This next image indicates elements of this drainage system, in which we see base drains that proceed underneath Dike 1, and we see additional drainage galleries, which are required to handle water within the reservoir, in addition to that flowing through the sand structure. Between the time the dam entered operation in 2008 and the failure, there were a series of events that are relevant to understanding the condition and structure of the dam on November 2015, November 5. First, there was a redesign of FUNDãO's drainage system in 2011 and 2012, which followed the sealing of the base drains. As you can see in the next image, water began seeping out of the dam and eroded the area surrounding the base drains in April of 2009. These seepages indicated that there were construction flaws in the base drains. The base drains were sealed because they could not be repaired. In order to replace these drains, a new drainage component, a blanket drain, was constructed just below the crest of Dike 1 at elevation 826 meters. This next slide illustrates the new drain. A blanket drain is a layer of pervious material that's placed on a foundation to facilitate drainage. As you can see, the new blanket drain had a series of pipes called cannonets that would provide additional drainage and facilitate the collection of water from the blanket drain. The cannonets are illustrated in the figure by the red lines. The blanket drain was different from the base drains it was intended to replace. In particular, the base drains were expected to drain all of the sand tailings, but the new blanket drain would not drain the tailings located below it, that is, at elevations below 826 meters. The next series of events concerns the main and secondary galleries. In mid-2010, tailings were discovered to be entering the drainage galleries, which indicated they were not working properly. After repair work commenced on the main gallery in January 2011, an overflow channel was opened between Dike 2 reservoir and the Dike 1 reservoir, and that can be seen in this image. This overflow channel permitted surface water to move from the Dike 2 reservoir to the Dike 1 reservoir for drainage through the secondary gallery. However, the water behind Dike 2 also contained slimes. This meant that slimes entered the Dike 1 reservoir through the overflow channel. That is indicated by the red coloring. In addition, During the period in which the galleries were being repaired, the beach behind Dike 1 was at times less than 200 meters wide. This will become important to understanding the conditions at the left abutment on November 5, 2015. By July 2012, it became evident that tailings were continuing to enter the galleries, which meant the repairs were not successful. As a result, the repairs were stopped and plans were made to plug the galleries with concrete and replace them with other drainage systems. Around the same time, structural concerns about the secondary gallery, which ran under the left side of the dam, led to the conclusion that the dam could not be raised any higher in that area. To avoid placing additional weight over the secondary gallery, which might have overstressed it, the crest of the left side of the dam was moved upstream or set back. Building the crest of the dam along the setback allowed access to the secondary gallery for plugging and prevented further weight from being placed on it. As raising the dam continued with the setback in place, a plateau resulted above the secondary gallery near the left abutment. The last relevant event occurred in August 2014, which is when a series of cracks were discovered on the setback, along with seepages being observed. The locations of these cracks is illustrated in this image by the yellow lines. To address these cracks, which were indicative of instability, a reinforcement berm or a layer of compacted sand was constructed in front of the setback as shown in this diagram. Additional monitoring equipment called piezometers was also installed to measure the level of saturation on the left abutment. It should be noted that the cracking is what we would call slumping and was not itself indicative of a flow slide, but nevertheless was symptomatic of the increasing saturation within the body of the dam. Turning now to the three questions, as I mentioned before, that the panel regarded as central to answer to explain the event that occurred. Let's turn to question 1. Why was the event a liquefaction flow slide? The answer to the first question, simply put, is that the sand tailings in the dam were able to liquefy and flow because they were loose, uncompacted, and saturated. There are three conditions that are necessary for a flow slide like the one at FUNDÃO to occur. The first is loose, uncompacted sand that is likely to contract when placed under increasing stress. The second is saturated sand tailings, and the third requirement is a triggering mechanism. These conditions were found to exist at the dam. First, the sand tailings are placed in a relatively loose and uncompacted state as a result of the method of deposition being pumped and not compacted during raising the dam. These materials shown in laboratory tests, shown in field studies, reduce in volume, that is, contract, when additional weight is placed upon them. Now, normally, this aspect of the FUNDÁO sand tailings is not a concern when the sands are dry or unsaturated, when they behave in a reliable way. However, when they become saturated, sands can become much weaker and become susceptible to liquefaction failure if more weight is placed upon them under certain stress conditions when deformations arise. The second condition is a saturation of the sands, as dry sands are generally not susceptible to liquefaction. In this regard, the original drain stack design concept was not in principle amenable to liquefaction, and the explained design changes brought about an extent of saturation not anticipated in that concept. The new design allowed saturated conditions within the tailings, as evidenced by the extensive system of piezometers intended to measure it and limiting criteria established to evaluate it. The key to understanding the degree of saturation at the FUNDÁO Dam is understanding the drainage blanket that was put in place after the base drains failed. The blanket drain was the principal drainage mechanism for the dam on November 5, 2015. As the dam was raised upstream, the volume of sands that the blanket drain was required to drain increased. As the reservoir grew, the distance between the tailings that needed to be drained and the blanket drain also increased. Over time, as the dam increased in height, the blanket drain was less and less effective at draining the sands, and thus the degree of saturation of the tailings increased. Let us look at what the panel's modeling of water conditions in the FUNDÃO Dam over time showed. In the next slide, the yellow area indicates the blanket drain, and the white area above it and outlined with a thick black line represents the portion of the dam to be drained by the blanket drain. The blue area indicates the downstream slope of the dam, that is the face of Dike 1. These slides show that as the dam's reservoir grew over time, the blanket drain became more and more distant from the tailings it was intended to drain. The panel's models show that the blanket drain at elevation 826 meters became less effective over time, and as it did, the saturation level in the dam increased. As I mentioned, saturated sands is one of the requirements for a liquefaction flow slide. Saturated sands can lose their strength and eventually collapse when force is applied on them or stresses are removed from them. This loss of strength takes place rapidly. Let us turn to question 2. Why did the liquefaction flow slides start at the left abutment and not the right abutment? Once we determined that the conditions for a flow slide existed at FUNDÃO, the next question was why did the failure occur where it did? In other words, what was unique about the left abutment or different from the right abutment? In short, our analysis led us to conclude that the flow slide occurred at the left abutment because the setback at the left abutment had been built over a mixture of sands and slimes and not just sands. The left side of the dam was different from the right for two main reasons. First, there were layers of slimes underneath the left side of the dam. And second, the setback on the left abutment moved the crest of the dam above the area where the slimes were located. As we said earlier, the dam's design intended that slimes and sands be physically separated and required a 200-meter wide beach of sand tailings to ensure that the slimes were adequately contained. This would also allow the sands behind Dike 1 to drain freely, unimpeded by the slimes. However, over time, the slimes encroached into the Dike 1 reservoir. These slimes came through the Overflow Channel connecting the Dike 2 reservoir and the Dike 1 reservoir that I mentioned before. Beginning in mid-2012, the crest of the dam on the left side was set back to allow repairs to the drainage gallery there. The setback was being built on top of previously deposited slimes. We confirmed the presence of slimes underneath the setback. As you can see in this image, we tracked the location of the slimes over time using aerial photography. We then superimposed a later in time image of the dam with a setback over the slime's location. The slimes are in red, and the setback is drawn in white. As you can see, the setback is on top of the slime's layers. The presence of slimes beneath the setback meant that the sands above them were not able to drain freely because the slimes impeded their drainage. As a result, the left abutment experienced higher levels of saturation. The slimes were also weaker than the sands. As we'll see in a moment, these slimes layers under the left abutment played an essential role in triggering the failure. This slide, the next slide, compares the section of the left abutment and the right abutment, and the presence of slimes is minimal in the right abutment and fully confined, emphasizing the role of slimes contributed to initiating failure at the left abutment. Question 3 is why did the liquefaction flow slide occur at the left abutment on November 5, 2015? This final question concerns the timing of the collapse. That is, what triggered the collapse on that date? The only trigger that was fully consistent with the evidence available to us is something we called lateral extrusion, which I'll explain as simply as I can, considering its complexity. As I've discussed previously, there were saturated loose sands in the dam, and underneath these sands, under the setback, at the left abutment, were layers of soft slimes or layers of slimes incorporating sands. As the dam was raised, more weight was placed on the slimes, which caused them to be pushed forward, outward, in other words, to move laterally. This process is similar to squeezing a tube of toothpaste. The toothpaste pushes out of the tube while your squeezing is in another direction. Hence, the weight of the sands was pushing the slimes forward in the direction of dike 1, in other words, in the direction of the face of the dam. This diagram is a simplified illustration of the lateral extrusion process. The large arrows pointing down illustrate the weight being placed on top of the slimes from the sands above them as construction proceeds. The red arrow pointing to the right illustrates the slimes being pushed forward or outwards towards the face of the dam progressively as the weight of the sands increased. The process was slow, and the daily movement of slimes toward the face of the dam would have been unobservable to the human eye. As the slimes pushed forward, the sands above them moved with the slimes, were dragged with that movement. But the sands, unlike the slimes, are not cohesive, and this dragging process would result in a reduction of confinement, and the pressure of confinement would reduce in the sands until they collapse. Modeling confirmed this. We undertook compressed comprehensive computer models that embraced all of these physical processes, as did experiments to simulate the conditions during extrusion resulting in the abrupt collapse of the sand tailings. We're about to see a video of an experiment in the laboratory that replicates the stress conditions in saturated sand while the stresses involved in its lateral confinement are being reduced by extrusion. Watch the video carefully and you'll note the collapse occurs in a very abrupt manner. There is one final piece to the panel's analysis, and that is the earthquakes that occurred on November 5th. 3 earthquakes took place shortly after 2 p.m., and their epicenters were located as estimated within a few kilometers of the Frontal Dam. The largest earthquake was at around 2:13 p.m. local time and measured at a magnitude of 2.6 on the Richter scale. We consulted with our consulting seismologist to determine the likely ground motions occurring in the vicinity of the Frontal Dam resulting from these earthquakes. The ground motion is the movement of the Earth's surface that results from an earthquake. These movements are then used as a loading into our analyses. There's a good deal of uncertainty around these ground motions because there's no seismic monitoring equipment close to the dam site. As a result, the seismologists extrapolate the likely ground motions in the vicinity of the dam based on measured ground motions of earthquakes that occurred after November 5th that were detected using seismic monitoring that was installed after the failure, as well as using additional procedures that they use. We use the model discussed before to assess the effect of the earthquakes on the movement of the slimes beneath the setback. The computer model showed that small displacements would occur due to the earthquakes, likely accelerating the lateral movement of the slimes and potentially accelerating the failure. To summarize our conclusions, the failure of the Frontal tailings dam by liquefaction flow slide was the consequence of a chain of events and conditions. A change in design in 2011 and 2012 brought about an increase in saturation, which introduced the potential for liquefaction. As a result of various developments, soft slimes encroached into unintended areas on the left abutment of the dam, and the embankment alignment was set back from its originally planned location. As a result of this setback, slimes existed beneath the embankment and were subjected to the loading as raising developed. This initiated a mechanism of extrusion of the slimes and pulling apart of the sands as the embankment height increased. With only a small additional increment of loading produced by the earthquakes, the triggering of liquefaction was accelerated and the flow slide initiated. We hope this presentation helped provide an understanding of the technical reasons for the dam's collapse. This concludes my overview of the panel's report issued today on the immediate cause of the failure of the FUNDÃO Dam. Thank you.